So just to recap again what I just said, we're shining a laser into glass, and we've noticed that as it gets to this point where it's about to go into the glass, the light stops going the direction it would have gone. So let's just see what direction that would have been. If it's just air into air, it of course is just a straight line. But when I change the second material to glass, it changes direction. We want to avoid saying that it bends, because light is not a solid object. Light is something moving, and then it stops moving that direction, it changes direction. This dotted line, which doesn't need to be dotted but often is called the normal. So there's a few words in waves that are a bit confusing. We've come across the word normal before in everyday life, but this is not the adjective normal. We're not saying this line is normal, we're saying this line is the normal. So it's a noun. And we draw the normal at the point at which the light is entering this new substance. It was in air and now it's going into glass. The point that separates the first substance from the second, we call the interface. So this horizontal line is the interface between air and glass. The place that the light is moving through, for example, the air, is called the medium. Another confusing word, because once again, this word medium is a noun. We're saying the medium is air. We're not saying it is like medium as opposed to large or small. And the medium here is glass. So the interface is the line between the two mediums. We draw the normal at the point at which they cross into the medium and perpendicular to the interface between the two mediums. And then we draw an angle from this ray here. We should also be drawing arrows on it to show the direction of the light. This arrow we call the ray. It's a ray of incidence. We can also call it the incident ray. So we draw an angle between the ray of incidence and the normal, and that angle is called the angle of incidence. And then we have the reflected ray, or the ray of reflection. Reflected ray. And so this angle is going to be the angle of reflection. And I'll take a screenshot of this and put this on your whiteboard afterwards. Angle of reflection. Or what I might do is get you to label it yourself from memory, we'll see. So yeah, angle of reflection. Okay, what was I going to do next? Okay, so yes, the next thing I was going to say is, how do we think these angles might appear? So you don't have to say anything, but think in your head, how do you think they're going to appear? I'm going to do a little experiment to find out how they're going to appear. I'll choose that. Click on angles. They're the same. So the angle of incidence is always equal to the angle of reflection. This is known as the law of reflection. The way they might test this is they might get you to complete the diagram, and then they just want you to make sure that you draw the reflected ray roughly so as the angle of incidence is equal to the angle of reflection. You don't need to get a protractor out. It just needs to look roughly the same angle by eye. Now, next is this angle. We might be able to, again in your head, have a think about what you think it's going to be. What do you think I'm going to label this ray as? And what do you think I'm going to label this angle as? So this ray is called the ray of refraction, because that's what's happening here. We're refracting the light, which is what happens when the light, or actually it happens with all waves. When a wave moves from one type of medium into another, it changes direction. And then we have the angle of refraction. We call it the refracted angle as well. Angle of refraction. So, okay, yeah. So we've got, okay, so what else do we want to notice about this? Well, we probably want to notice that we have this index of refraction. Now we're getting a little bit more advanced. And this might be something you could experiment with yourself. So index of refraction. And we've got and for air it's 1. It's actually a little bit different. I think it's slightly more than 1. A vacuum is 1, and air is only tiny bit higher than 1, because it's only slightly different to what it is in a vacuum. And then we've got it for glass, which is roughly 1.5, depending on what type of glass it is, really, but roughly 1.5. So I think I will just give the game away, actually. Basically, you can see that we're moving from a low refractive index. Refractive index is n, so we've got a lower n, not necessarily, and to a higher n. So a higher refractive index. And when we move from a low to a high refractive index, the light changes direction and moves towards the normal. So we have another normal underneath. Okay, it moves towards the normal. It was going to be over here somewhere. The light would have gone to about here, but it moved towards the normal. Okay, I'm just going to. I think I might just stop the video there, actually, because I think that pretty much sums. Actually, no, I won't stop the video there. I'll pause it. So let's have a look. I think I can put that back now. Yeah. So we've gone from a low refractive index to a high refractive index. Let's turn the laser off. And this time we'll go from a high refractive index, this time water, which is not as high as glass, but we're going to go to air. So we're going from a higher to a lower refractive index. And then turn the laser on. And we can see it now moves away from the normal. Okay, so we can actually change this to air, and it's just a straight line. And when we change it to water, it moved away from normal, and we still have the reflection. So that's something else we want to understand. I think I'll stop the video there, actually, and I'm going to get you both to do a little bit of experimentation with this to see what else you can discover about it. Okay.